Now? Okay, very good. Thank you, Akash, for invite. Go ahead.
I was going to introduce you, but I guess you don't need an introduction.
No, please go ahead.
I was just going to say it's my pleasure to have Shaz Qadeer here give this talk to us. Shaz has always looked after software developers who have struggled with building large systems, especially to deal with concurrency. And so he is here to tell us some of that. All right.
Okay,
now you
very
can start.
Good. Thank you. Thank you, Akash. Thank you for inviting me. So I want to tell you about my work on the Civl verifier. Civl is a verification system for working with the concurrent programs. Its goal is to make it feasible to scale verification of concurrent programs to large systems. In a way, I've been working on Civl for about 20 years. The things that exist today in the Civl verifier, as it stands today, some of them were invented about 20 years ago, and after repeated attempts and repeated failures and some partial successes, a whole bunch of ideas came together that can work harmoniously together, and that's this verifier in its current form. There's a website which has a bunch of documentation for the verifier. It's listed here, and if any of you feel are inclined to give it a shot after hearing this talk, I would love to hear your feedback. And if you want it to do things that it doesn't do right now, I would like to hear that also. In the middle of the talk, I will talk about oops, sorry, I'm getting some. Was there a question?
No, I think it was just someone's mic was not muted.
In the middle of the talk, I will also talk about the big open problems that are that need to be solved if we want to get systems like these kind of verification systems in the hands of engineers. There's a long even though there's a long road behind me, there's still a even longer road ahead of all of us. Okay, so without more introduction, let's get into the talk. So so here's a very simple concurrent program. It has two threads. Before the threads are launched in parallel, a shared variable X is initialized to a constant N. So the idea is that N is an arbitrary input to the program. Both threads are doing the same thing. They each acquire a lock. And within the critical section, they read the value of X into a local variable, increment the local variable, and update X to the new value. Then they release the lock. And the goal is to prove an assertion at the end when both threads are finished that X is equal to N plus 2. Okay, so ignoring, like modern advances, if you look at the classical approach that has been espoused for, the last 50 years of research in concurrency, where you're actually trying to verify safety properties, it boils down to this thing that I'm showing on the right side of my slide. The idea is that, well, every program is a Turing machine. Every Turing machine has a transition relation. You write down the transition relation. Okay, it modifies states. It has some initial predicate. Then you invent an inductive invariant, and then you prove that the inductive invariant is preserved by the initial, is satisfied by all the initial states and is preserved by that transition relation. And then if your inductive invariant is strong enough to discharge the safety properties, you're home free. Now, this is a very general approach, but unfortunately, it is very difficult to use in practice. So the problem starts, and this I cannot overemphasize this issue, is that when you compile down to a transition relation, you have only you have only one choice left at this point. You invent the inductive invariant completely automatically. Because if you want to involve the programmer at that level, then there is no chance, because you have lost all program structure. Second thing is that if you are approaching the problem of reasoning with invariants at such a low level of detail, you're going to end up invariably with very complicated invariants. So your chances of getting any automation are out the window. Okay, so in Civil, this is not what we do. So we are going in a completely different direction. We recognize that structure is important, and we have to play with the structure throughout the verification process. So Civil works by iterative simplification. That's the core idea. So the idea is that, okay, well, you start with this program. That program is kind of hard. Why don't we try to simplify it? So we take one step of simplification. So we recognize that, well, actually the programmer is doing all this locking, etc., to create atomic sections. So it ought to be possible to show that the program on the left is similar to the program on the right, where we have slapped an atomic block across around the code of both threads. So the idea is that these two atomic blocks execute without interruption, one before the other in some order. Okay, so the program has been simplified. We have larger atomic blocks. Now we can do another round of simplification. We recognize that, well, for an atomic block, we can reason in isolation without worrying about what the environment is doing. So we can summarize the atomic block. So this means that each of those blocks is simply incrementing X and atomically in one step. And we can eliminate, we can hide the local variables T1 and T2. We can even hide the log. The log has done its job. So we can hide those variables. Okay, so the program has become simpler. Now we can simplify it even more. So we recognize that if you have two increments happening in parallel, they might as well happen sequentially because the order doesn't matter. And finally, we have a sequential program, and that's very easy to verify, either by a human or automatically. Okay, so this is the general story. And this example might seem very trivial to you, but I want to assure you that this is simply the tip of an iceberg. If you want to move towards realistic implementations of large concurrent systems, you are going to face this kind of problem over and over again in a much larger context. Okay, so we have to. This is what I'm pointing to is very fundamental. Okay, so the general idea, as you have seen, right? So we are operating with iterative simplification, where you manipulate not one representation of the program, but multiple representations. So the way Civil, the theory behind Civil is that of layered refinement over structured concurrent programs. So we manipulate lots of versions of a program at the same time. So they are shown here in the stacked manner. The most detailed implementation is P1 at the bottom, and then you go, you simplification or you do abstraction, and you keep going up in that stack, and you get up to PN. And the idea is that you can stop anywhere you want. Okay, when you think that you have reached a point where things are obviously correct, because each transformation, each layer is discharged separately. You can choose different methods at each layer. You can even choose to leave some layers unverified. You can do either an invariant-based formal proof. You can do some kind of best effort testing at a layer if you so wish, right? So basically the idea here is that these layers give you a kind of decomposition where different aspects, different tricky aspects of the program are being sorted out at different layers. And this makes it easy to split your thinking and also bring different kinds of techniques to bear at different parts of for different parts of the verification. Okay.
Yeah. So can I ask a question?
Of course. Yeah.
So
go ahead.
You talk about, so concurrency, you're going to assume to be shared memory concurrency, fixed number of threads, or what is your starting point?
It is shared memory concurrency. But there is no requirement that there should be fixed number of threads. There will be arbitrary number of threads, and the basic model is that of global shared state that can be manipulated by gated atomic actions. I'll talk about gated atomic actions later. It's very general. So, for example, even if you have a distributed system, you can model it in the same way.
So. Okay, so you said that, but but does it really work that way? So if you have message passing kind of systems, so I'm trying to put Ivy, in relationship with this kind of work. So, I mean, I would think typically in distributed systems, you will not be thinking, I mean, that will, this abstraction with atomic blocks, that is not something that the developer would have in mind at the time when you're writing a message passing protocol or something like that. You have different kind of a mental model in mind.
Well, I mean, I think that, you're right. You're right that at the very lowest level of abstraction, you have a lot of message passing and channels and messages flying over. And you may have to model buffers, for example, where messages have been stashed, messages can get lost. But I think that if you are doing some kind of an abstraction, very soon you get back into this model of shared state. As far as, so I mean, let me give you an example. Actually, the example is right in the next slide. So why don't we just go there? So you're asking about message passing, right? So Paxos, let's look at Paxos. So Paxos is a verification that was achieved in Civil. Now, it was a multi-layered verification. At the lowest level, you have message handlers that are executing on a single node. Of course, the message handlers are maintaining some shared state, right? Because once a message handler finishes, the state remains until the next invocation of the message handler executes. So you have shared memory. But as you pointed out, you also have message passing because these nodes, they are sending messages to each other, all the Paxos messages. So then that means that we have a state residing in channels also. But those channels are also shared state at the level of the modeling that we have there. So that's the lowest level implementation. Then what happens is that you abstract it. So then you get to the kinds of protocol descriptions that you typically see verified in papers, where you have some global variables and you have large atomic actions or transition relations and so on. And then you do further abstraction where all of that complexity disappears and it appears as if consensus was achieved in a single atomic step. Okay, over the thing, the shared variable. So the way, how do you model that? Well, the way you model it is that there's a shared variable, there's a variable residing at each node. And atomically, by magic, it's as if a single value got populated in each one of those variables. So am I making sense, Akash?
Yeah, so, okay. So I think it's interesting that you can do examples like this. I was going to say that surely you can't do something like Paxos, but you're saying...
Yeah, so, yeah. And I think it's because I chose to simplify things too much by giving you this picture. The reality is that in addition to these kinds of things, there are other tactics that natively deal with the message passing. And they were, they were invented when an attempt was made to model message passing systems. Yes. So this picture on this slide is very much classic Civil, but yes, it is there's more stuff in there now to deal with message passing in a convenient way.
Okay.
So is every concrete implementation a single thread? I mean, a sequential program?
No. Concrete implementations would be highly complex concurrent programs.
Okay.
And typically the abstractions tend to become simpler and simpler.
Okay, thank you.
Okay. Okay, so we talked about one case study, Paxos. The other one that was pretty interesting and challenging was the concurrent garbage collector. So here there are even more levels, not surprisingly, because there are the operations that they are even more fine-grained just because of the nature of the problem. So you have very, very, very fine-grained atomic operations at the lowest level. And then you have a mixture of logged accesses and read-write accesses to get small critical sections. Then there's multiple kinds of synchronization happening in this garbage collector. So one of the kinds of synchronization is barrier synchronization. Then there's the phase change business. And then there is the actual search that is happening when you're collecting garbage, which is a kind of depth first search. There's the complexity of root scans and so on. So, there's a lot of machinery, a lot of layers there to deal with all that stuff. Okay, very good. So let me give you now, the next level of detail. So far I've been talking at a very high level. I'm going to give you a little bit more detail now about how all this kind of stuff is actually accomplished. So I showed you this tactic, right, which creates atomic blocks. So I'm sure everybody by now knows about this business of commutativity reasoning and mover types. So the idea is that you allow programmers to express mover types for your atomic operations that your program is composed of. And there are two kinds of primitive mover types, right movers and left movers, in addition to operations that don't commute at all. And once you have that kind of labeling, then you use this very simple theorem attributed to Richard Lipton, that if you have a sequence of right movers followed by a sequence of left movers, then you can pretend as if that sequence executed in one single step. So the idea is that the right movers and the left movers, they're all executing in being done by one single process or thread. Okay. So that's the idea here. So here, acquire is a prototypical right mover, release is a prototypical left mover, and protected axes they're both left and right movers. We call them both movers, for example. So in Civil, you have at every layer, the program is a bunch of procedures, possibly dynamically created, possibly asynchronously invoked, possibly in parallel invoked, that bottom out at these primitive atomic actions. Those atomic actions, the programmer can specify what their mover type is. Civil uses commutativity checks, logical commutativity checks, to make sure that those mover annotations are sound. And then it does some kind of flow analysis to check that the atomic blocks that are desired, they actually satisfy this condition, right movers followed by left movers, and that's how it creates atomic blocks.
So Shaz, could you remind us what are these left and right movers?
Sure. So a right mover, like if you look at this picture here, where my cursor is hovering, it's an action that commutes to the right of any action done by the environment. So here, the arrow in black is an action done by the black thread, right? The white is some action it's done by the environment, and the final state after executing both of them is the same as if the white thing executed before the black thing. So we can move the right mover ahead in time. Left mover is the other way around. Does that help, Deepak?
So right mover means basically you can interchange the two statements and you get the same resulting state, is it?
Yeah, that's correct.
Is it like what are those called? Like commutative or independent events? They're like independent.
Yeah, events. But there is directionality. There is directionality here. So it's going in one direction. If you have a right mover occurring before an arbitrary action, then you can swap them. But if the right mover occurred after the arbitrary action, you can't move it before. Similarly, the left mover can be moved before, but not after.
Mm-hmm. So why is acquire a right mover?
So you can do the math, of course, by looking at the logical specification of acquire, but intuitively, the idea is that, well, if what can an acquire conflict with, right? It cannot conflict with something that doesn't touch the lock at all. So there's only two operations that touch the lock: acquire and release. So acquire followed by acquire cannot happen just because of the nature of the beast. So you don't have to do anything about proving that commutativity happens in that case. Supposing acquire by one thread is followed by release of a different thread, then the second release is going to fail because there is an assertion gating it that, I hold the lock, but, clearly it does not hold the lock because the other thread just managed to acquire it. But if you move the release earlier, the assertion will continue to fail because it's saying I'm hold the lock, and the acquire succeeded. It means the lock was not held. Things like that. So in both cases, the second guy fails, and the lock ends up being acquired by the first guy. This kind of argument.
So the way I think about acquire and release being right and left is that in a critical section followed by one thread, you can always squeeze out the actions of the other thread if it's well nested. Right? Anything the other thread is doing in between, you can squeeze out because it's not going to conflict.
So it is not clear. This is Raghavan. It is not clear to me why, say, C and D can be moved out of the way of B and E.
No. You never move. Sorry, you never move around actions of the same thread. You're only trying to squeeze out actions of a different thread. Okay. Here, if you look at this sequence, right? So black actions are done by thread 1, and white actions are done by all other threads. You're not trying to swap actions done by the same thread. Does that help?
Okay.
Yeah. Shall I continue?
Yes, you can continue, I think.
Okay. So one other tactic is creating atomic actions from atomic blocks, right? So the general story here is to do some kind of a simulation proof. Okay. So imagine that you have a procedure in which there is fine-grained concurrency and interference. So you see those comments where I say yield. So yield is, the thread that's executing this code yields to a different thread, allows another thread to switch in. There's a context switch. So what we want to, and CAS, I'm using the word CAS here. CAS is compare and swap. So it checks whether B is equal to false. And if B is false, then it sets B to true. So that entire thing happens atomically. And if B was set to true, then it returns true. Otherwise, it returns false. So we want to show that, there could be unbounded computations here and whatnot, but it really behaves like this action on the right, in which at some point atomically B happened to be false and B was atomically set to true. Okay. So the idea is that you try to show that every execution of the procedure on the left side behaves like skip, arbitrary number of skips followed by exactly one occurrence of the atomic action on the right side, followed by arbitrary number of skips. And you can see, that this is really true because either acquire is moving around inside it without any observable change. It's only moving its program counter, or, it actually examined some global variable, but left it unchanged. So if it did not modify the global variable, then, nobody else can observe it. And then at some point, the CAS succeeds. And the successful execution of CAS is pretty much like what this atomic action on the right side is. So that's the intuition for how the simulation works. And Civl basically does all the low-level work in generating verification conditions to check the simulation. Okay, so that's yes.
So I don't understand. Suppose B was originally true. Then S will always be assigned false, right? The CAS will fail and S will be assigned false. So it goes in an infinite loop. So what is the simulation? I didn't.
That would be simulated by skip star.
Okay.
Yeah, so that you never get to acquire. So basically, this is this thing, every sequence should follow this, but it's not a total correctness proof here.
Okay.
Yep.
Okay. Yes. Thank you.
All right. Then, we also want to be able to change the state representation. This is very critical. So for example, on the left-hand side, we have an implementation of lock using a Boolean variable B. But for higher level reasoning, for clients of lock, we would like to have a logical specification of locks where we actually stash inside the lock the ID of the thread that holds it. Okay. So here we are changing the representation of the state of lock. But it's no big deal. It's a small variation on what we did earlier. All we got to do now is, before we do the simulation check that I talked about earlier, we allow the programmer to introduce state in computation. So here the programmer has to introduce a parameter. So you have to pass into acquire the thread ID. And then at the point when the lock acquisition has happened, you introduce the computation that sets the abstract variable L to the appropriate value. So you introduce parameters, you introduce new global variables, which represent the new state, and then you introduce the computation that updates the freshly introduced variables. In all of this, you got to make sure that you are not actually introducing computation that modifies existing variables. So Civl will check all that. There's the new program in which all this fresh computation has been introduced must be a conservative extension of the old program. And there are checks that are performed to make sure that that happens. And now you actually do the simulation proof on this augmented program. And there, the idea is that, well, you're introducing L and you're hiding B. So when you are checking for the atomic action happening, at that point, you ignore changes to the hidden variables. And you only pay attention to the variables that continue to exist at the next layer. Okay. So here, there is a gotcha, which is that on the concrete side, on the left-hand side, the blocking inside CAS is based on B. But on the right-hand side, the blocking is based on the value of L. So obviously, something else has to be provided. And this something else is the information about a coupling invariant. So there's an invariant on this augmented program that B is true if and only if L is not equal to none. So the programmer specifies that also. And once you have that, then the proof will work. Okay. All right, I'll continue. Okay, so this tactic is the tactic that was introduced when we wanted to make Civl work conveniently with message passing programs. So often in modeling message passing programs, you just want to think about launching and some computation that executes asynchronously. Okay, so Civl has a primitive for doing asynchronous calls, and you can asynchronously call procedures at concrete levels, but at abstract levels, you can also asynchronously launch atomic actions. So here's a very simple program in which you only have atomic actions. Okay, so there's an atomic action async sum. And so there's a shared variable X, and async sum launches n copies of add operation asynchronously. So you're doing add 1, add 2, add 3, add 4, like that. So even though you have only atomic action, there's still a lot of executions possible, right? Because the different copies of add, they're atomic actions. So there's a pool of atomic actions and they can execute in any order. So here, for example, I show you 4 different executions in which the different add instances are executing in different orders. Okay, what we want to show is that no matter how these instances are interleaved, you always end up with the x return containing x being incremented by the sum of first n natural numbers. Okay, so that's what is captured in this action. So we want to show that action async sum, it somehow refines or behaves in the same way as action sum. So again, you can make a commutativity argument here. You can say that, okay, well, all these asynchronous executions, they're all equivalent to the first execution, in which the sequence of adds is happening in a particularly convenient manner, which allows us to write the induction hypothesis or the inductive invariant in a convenient way. And then for this particular execution, which is still unbounded, right? Because its length depends on the parameter n, which can be unbounded. You write an inductive invariant, which guesses a j. J is how far we have executed in this step. So how many more asynchronous steps need to be executed further. It updates x to the result of executing steps up to j, and says, okay, well, now we have j plus 1 to n asynchronous steps still remaining. Okay, so the programmer has to specify this, and then Civl does all the plumbing work of making sure that this kind of asynchronous invariant is inductive. Okay. So just to connect this to,
so sorry, Shaz, what was that invariant, the sum invariant again? No.
Yeah, sure. Okay. This invariant here.
So you're trying to show that this async sum works like adding up like this the sum action for
Correct.
all n, is it? For all n.
Yes, for all n. Yes. So what I have to show is that I have to eliminate the asynchrony inside async sum. So what I have to do is I have to show that async sum is a refinement of some invariant. You see why? Because I can choose j to be 0, and for that choice 0, some invariant is identical to async sum. Do you agree?
Mm-hmm. So j is what? J is j between 0.
J is chosen. So j is a variable. It's a local variable, right? Local variables are initialized non-deterministically. So I can initialize it to whatever I want. So I can in fact initialize it to 0. So the first argument is that if j is 0, then async sum is identical to some invariant.
Why?
Well, I mean, let's choose j to be 0. So this assume becomes assume true. This x becomes the update to x is vacuous. There's no update because j is 0, then you're assigning x to x. So you can remove that. So the assume is gone, the update to x is gone. And then if you look at the for loop, that is going from for I in 1 to n, because j is 0, async add I. That's exactly the code in the async sum.
So sum invariant is just saying that you sum the initial j of them.
Yes.
I mean, you sum the initial j of them, and then for the remaining you do async.
Correct.
Okay, so you're saying when j is equal to n, then it will just get sum.
Exactly. So when j is equal to 0, you'll get async sum. And when j is equal to n, you'll get sum. And now you have to also show that this invariant sum is inductive. So to do that, you have to now say that, okay, well, if you go from an arbitrary j to j plus 1, then you have to now take the definition of add, the add action itself. And then, so you take sum in, and after that you execute one step of add, then you have to show that that thing refines some INV with j set to j plus 1. Okay, let me continue.
Yeah, you go ahead.
All right. So here's an important slide. Remember that I was talking about how you have all these layers of programs, and they're all structured programs. So another thing that is happening in Civil is that all those layers are represented together in a layered concurrent program. So this is, how these programs, these layered programs look like. So you have layer annotations on shared variables. So for example, this annotation on B at 0,1 is saying that, well, B got introduced at layer 0, and it was it stayed around until layer 1, at which point L was introduced at layer 1 and it stayed around it until layer 2 and so on. Okay, so where global variables come and go. Similarly, atomic actions come and go. At every layer, there's a pool of atomic actions. And if you don't need an atomic action, as you go up, which can easily happen, you eliminate that atomic action from consideration. You garbage collect it. Similarly, procedures come and go. So, at the very lowest level, you will have all these procedures there, right? Because lots of detailed computations are happening. But as you go up, procedures will disappear. They will get converted into atomic actions. So call to procedures will get converted into calls to atomic actions. Those procedures are not needed anymore. Those procedures also get garbage collected. So that's how, programs get simplified. So what happens, the reason you need layered programs is that, these programs at multiple layers, there's a lot of sharing between them because, programs gradually, disappear piecemeal. So for a while, you're reusing parts of the program over and over again in multiple layers. So that's why this gives you, compactness, compact representation across multiple layers. Okay, 709. Let's keep going. So, all right. So there are some very foundational things inside Civil. So I'm now moving into the next stage of the talk where I'm going to give you a little bit more detail. So one of the things that is very important in Civil is its notion of how a primitive atomic step is specified. And that is done using gated atomic actions. So everybody knows about atomic actions, right? It's just another way of specifying a transition relation. Dijkstra introduced guarded commands back in the day, many years ago. And that remained the way in which how you specified atomic actions for years until we come to gated atomic actions. The main innovation in gated atomic actions over and above guarded commands is that they have a gate in addition to blocking behavior. So the gate introduces the capability for the action to fail. So now an action can either fail or it can block, or it can successfully execute and effect a state change. Okay, good. Whereas, earlier in guarded commands, an action could either block or it could effect a state change. Okay, so gated atomic actions, right? They are able to capture all sorts of primitive things that you typically use in modeling programs. So you can model assignment, havocing a variable, asserts, assumes, and whatnot.
So what does it mean for the action to fail?
What does it mean for an action to fail?
Right.
I mean, it's the same thing as assert, right? Assert means that the program went wrong. You typically don't want that to happen. So the idea is that you're trying to prove a program correct, right? So the program will have assertions in it, and you're trying to discharge those assertions. And you want to make sure that those assertions never fail.
Okay, so it's like a guarded command in which you go to some failed state of it.
Correct.
You execute some.
Yeah. So you can imagine one way to model it is that there's a special state called bad.
Mhm.
And if you fail, you go to that bad guy.
Okay.
Yeah. Okay. So you can also very conveniently represent abstractions. So for example, the lock specification that I earlier alluded to, right, which captures inside the lock variable thread IDs and so on. So you can write the acquire spec and the release spec here. Interesting thing is that, it unifies precondition and postcondition, and it's a primitive for modeling both concrete and abstract semantics of programs. An important thing is the definition of refinement for gated atomic actions. So for guarded commands, refinement is very straightforward. It's just straightforward implication, because a guarded command can be modeled as a transition relation. So you just check. So T refines T prime, if and only if T implies T prime, for example. So for guarded atomic actions, because they can fail, gated atomic actions, it's a little bit more sophisticated. So A refines B, if and only if for every initial state S, if A goes wrong from S, then B must also go wrong from S. Okay, so if A fails, then B must also fail. And if B does not go wrong from S, which also means that A cannot go wrong from S by the first clause, and let's say A can take S to S prime, then B can also take S to S prime. So this is the foundation of layered refinement, because what this is saying is that as you go from layer to layer to layer, you can leave assertions unverified, as long as you have made sure that the remaining assertions capture all possible failing behaviors. So this is very important, because this means that you can verify the golden safety specifications at the lowest layer of the program piecemeal. Another very important thing in Civil is the treatment of invariants. So invariants are, of course, more sophisticated for dealing with concurrency, because you have to deal with the non-interference. So if a thread has a precondition, so let's before you go to threads, in a sequential program, right? If you write a precondition for a procedure, then you can just assume that precondition when you're reasoning about the code of the procedure, because the precondition was established by the caller. There is nothing else running, right, that can violate the precondition. It's not like that with concurrent programs. If your precondition refers to global state, then there is a possibility that somebody else switched in after that procedure was called and changed the value of global state, which now violates the precondition. So you have to worry about non-interference. So the foundation of non-interference reasoning in Civil is yield invariance. So a yield invariant is a separately specified invariant, very similar to a procedure. It has a name and it can be parameterized. And then you can refer to clauses inside it. So here there's a single clause. It says that a shared variable X is greater than or equal to the parameter I. Here's how you use it. Let's say you have a procedure, double link, and you have a concurrent program in which arbitrary number of copies of double link are running around, okay? So intuitively, we know that X can only ever be incremented. Now, how do we tell Civil that, Civil, X can only ever be incremented? And so you should be able to prove that a complete execution of double ink does at least 2 increments. So the way you tell Civil all that is that first you have to specify this invariant, yield X, right, which says X is greater than or equal to parameter I. You write a precondition which calls this invariant with the copy of X at entry. And then you write a post condition which calls that invariant with the copy of X at entry plus 2. Okay. And you can imagine how Civil will try to discharge this. Well, first of all, there is the non-interference part. You have to make sure that every atomic action or every indivisible fragment, non-yielding code fragment in the program preserves this invariant, which is true for this program, right? And then you have to use it, that invariant, in doing sequential reasoning. So that is done by, basically compiling away yield positions into a sequence of asserts, havocs, and assumes using the definition of the yield invariant. I don't want to go into the details, it'll get very tedious, but I hope you get the drift here, the general drift here. If you have some high level question, I'll take it.
Okay, so Shaz, this is similar to standard Oviki-Greaves reasoning, right?
Very good. Thank you. It's almost as if I paid you to ask these questions. Let's look at the next slide. So comparison to other approaches. So the general problem everybody has to solve is that if you have global state, So every concurrent program is going to have global state. And then there'll be threads or processes, and they will have local states, right? Now, some thread did some computation C1, it established some facts, then a yield occurred, and then it has to continue with C2. So what state changes are allowed here, right? So there are two components to state, G and L, right? So Owiki Greece is beautiful, right? It says that, oh, no problem. At the yield point, you can write an arbitrary logical expression referring to all global variables and all local variables. So this is very precise, but this is also verbose. And also because you have to write some logical expression at every yield point, okay? And the complexity is the size of the program times the number of location invariants. It's not only is it verbose, it's also expensive to check it. Then, Cliff Jones got into the game, right? And many years ago, all these things happened many years ago. He came up with rely guarantee. So he said, okay, well, why don't you just specify a rely condition? Because, a lot of the yield invariants, they are very similar to each other. And you can capture them just by the effect of all of them by talking about how the global state is being modified. And, maybe that can just tell you, what you need across a whole bunch of yield points. So you just specified a few rely conditions. And now you only have to check those rely conditions are being preserved by the program for non-interference. So this is good. This is an improvement. So you get compactness, you get more efficiency, but it also results in imprecision because the rely conditions cannot really reflect what happened locally inside what the information that got captured in the local variables of the programs. So then yield invariants are somehow able to split the difference. Okay. So they are inspired by both of these things. So they take the naming aspect of rely conditions, the idea that yield invariants are specified separately. They're given a name so that they can be called and reused. But they also take the idea from Owiki Greece that, these things should be context sensitive. So they should have access to local variables. So you have named yield invariants, which have parameters. So now when you call them, you can specify context local information there. So you get the precision of Owiki Greece and you get the compactness of rely conditions. Deepak, did that help?
Yeah, kind of. Yeah, I mean, I think maybe if you paid me some more, I'll agree that it's.
All right, let's keep going. Okay. Another very important thing in Civil is permissions. I can almost make a joke here. I'm telling you so many important things. Are they really that important? Because, if there are things were to be important, there should be very few of them, right? But how can there be so many important things? But I don't, that's what it is. That's what the reality is. Somehow, all these things have to be together. Otherwise, I'm not able to get the scale and the generality that I want. And by the way, believe me, none of these things was added willy-nilly. Everything was added after a lot of suffering and trying to do programs and trying to verify programs and failing to do it. So it's not like I wanted to add these things. Anyway, so continuing. Permissions. So why do you need permissions, right? So everything goes back to this new thorn in my side or in the side of anybody who wants to reason about concurrency, which is you have to reason about interference. When you reason about interference, you are immediately confronted with the problem of dealing with reasoning across multiple scopes. Because the condition that you want to prove is stable is declared in one scope. And the thing that can mess with it is happening in a different scope, right? When you have two scopes, you are trying to combine information from those two different scopes. Okay, this is very hard in reasoning in a tool that is based on syntax. If you look at, for example, classical sequential verification, when you're reasoning modularly about a program, you have precondition, and you have the code, and then you have the post condition. So you just have to look at, you generate a verification condition based on those components, and they're all, well scoped. They're all referring to variables in scope. So when you're combining things from across scopes, what happens if you have to introduce some constraint that refers to a variable in one scope and a different variable in a different scope? So that's a general problem. And in the worst case, you have no recourse, but to somehow reflect that information in the two different local variables into some kind of ghost global variable. But before you get to that worst case, there are some easier alternatives. And using permissions is an example of a technique that gives you easy proofs in many, many situations where you don't have to go to the ugliness of reflecting our local state into global state. Okay, so a permission is an ordinary program value. Just like normal values that you compute with. Permissions, you can think of them as they are embedded in a program variable. So it's conceptually, it's a function from the current value of the variable to a set of permissions, right? A fixed function. So as the value of the variable changes, the permissions embedded in it continues to change. Okay. And it's often its main use is to prove stability of yield invariance, because that's where you are mixing information across multiple scopes. So where's the scope business coming in? The thing about permissions is that you use a combination of linear typing and logical reasoning to get a very strong invariant. The invariant is that the permissions that are embedded in distinct variables across all scopes are disjoint. So this means that as variables are being mutated and parameters are being passed and values are being returned, permissions are not duplicated. If you started with disjoint permissions kind of move around among variables. They're only redistributed. They never get duplicated. And somehow, this thing seems to be very, very helpful when you are reasoning about non-interference across scopes. So because this invariant is is proved by a combination of typing and logical reasoning that sort of conceptually precedes the dynamic verification across executions, the invariant can be assumed in the verification conditions that are generated for non-interference reasoning. Okay. So I mean, that was all kind of vague, any question about that?
So again, are these permissions similar to ownership
Yes.
and VCC?
Yeah.
And...
Yeah, so they are similar to the closest thing is that they think about it as a lower level mechanism that allows you to conveniently encode things like separation logic or ownership types or things like that. So it's an independent thing, it's a lower level thing, but it allows you to. It's very much inspired by those kinds of thinking aids, and it allows you to encode them when you are doing logical reasoning. Yeah. Okay. So there are many open problems that need to be addressed. So yeah. So one of the things that I want to say before I talk about these open problems is that I have come to the conclusion that if you want that program verification, right, which is typically understood as the idea that program construction, writing the program, is an activity that is independent from program verification. One person is writing the program, sort of an almost a different personality is proving the program. This, I think, in my opinion, is basically a dead end. This is not going to fly. So instead of doing program verification, instead of chasing that dream, it might be worthwhile chasing a related but somewhat distinct dream, which is the dream of verified program construction. Because program verification, the idea that programs can be verified after they have been written has not, I mean, there are all experience has shown that this is too difficult. This is too difficult. So we have to somehow bring closer the thinking, the act of program construction and program verification. And what Civl is trying to do is build, some basic thinking aids, basic scaffolding, basic tooling that address the logical reasoning, the verification aspects of that unified endeavor. Okay, but the endeavor is much bigger than Civl, right? It's the endeavor of verified program construction. So in that, you need to make things, you need to really make things, you need to think about it in very much the same lens as, the way you think about building programming tools. So verification tools and programming tools, they are the same thing. So you have to talk about, just as you talk about program construction, program debugging, program maintenance, you also have to think about proof construction, proof debugging, and proof maintenance. Okay. And there are many, so once you think about that big problem, there are, more concrete problems within that domain that you have to address. Okay. Some of which I have listed here. Getting back to more concrete problems, you also have to deal with the issue of reliable encoding of composable finite types. Just like, I mean, today, if you look at, when I write programs, right, I define a few classes for sure, but a lot of those classes are essentially composing primitive types that are available as libraries. So I'm talking about vector sets and maps, and they're put together in various ways in various sorts of data types, and data types are nested and composed with other data types and so on and so forth. So just like all programming depends on this kind of composition, when we are doing verification, we'll be faced with making these things just as convenient to use and to verify with. And we are not quite there yet, right? Because these logical reasoning with composable finite types, to me, it's a very open problem to make it predictable. Reasoning about shared and mutable nested data structures is still, I would say, a big open problem, despite the number of papers that have appeared in the literature on things such as ownership types, separation logic, dynamic frames, and so on. I would say that still it's an open problem. More specifically for Civl works with layered concurrent programs, and I got to tell you, layers are a bit tedious. So it would really help if I write my programs pretty much as I would write an unlayered program, and somehow layers got inferred. That would be nice. That would really aid my productivity. So at this point, I'm at 7:30. I had some more slides, where I was going to show you some code and give you some more idea about non-interference reasoning and yield invariance and whatnot, but I'll stop here.
I had a question.
Yes.
So is verified program construction similar to program synthesis in the sense that you give a specification and then construct a verified program?
No.
Okay.
I mean, I actually don't know what program synthesis is. I mean, it could be that program synthesis could be a part of verified program construction, but to me, verified program construction is basically programming, right? Where you want to have much more confidence in the programs as you are constructing them. Now, that confidence could be achieved by synthesizing parts of the program automatically, but
Right.
They could also be achieved by helping by writing the specification and the program and showing the connection between them by doing more work if the synthesis is not working for you. Regardless, I would say that none of it is. I think that the point I'm trying to make is that just as nobody talks, just as we don't talk about automatic programming, right?
Right.
We should stop talking about automatic verification also. That's the main thing you should get from this. It's the whole thing: program construction, program synthesis, program verification. To me, it's just one activity, trying to construct a large system and having as much confidence in a very productive manner and having as much confidence as you can by putting tools in the right places and putting the human being in the right places.
Right. So just to extend on that, can you say that if you write a program, say a partial program and a specification, and you say place holes in some parts, and then you aim to synthesize some parts of it, can that be called a verified program
Of course.
construction? Okay.
Of course,
Okay.
of course,
Okay.
of course. Yeah.
Sure.
I mean, this layer inference, for example, right? This is just, you just gave me an example, a concrete example of that. So layer
Okay.
inference, any kind of inference is basically filling up of holes.
Okay. Okay. Yeah, sure. That
Yeah.
answers my question. Thank you.
Type inference is a kind of hole filling, right?
Okay.
Yeah.
Thank you.
Shaz, I had a question. So are there any program structuring techniques like STMs or whatever that would hinder your approach? Do you assume that the concurrent programs you start out with should be in a certain form? Are there
So do you have something in mind? Like what do you think could hinder it?
I don't know, some STMs or whatever, would these I don't know if they would.
By STM you mean software transactional memory?
Yeah.
No, of course not. I mean, STMs are beautiful, right? Because what they're saying is that if you can start with large atomic actions, and you can assume that the system will provide those atomic actions. So you don't have to refine those atomic actions further in yourself, because the system is going to provide them. So it's good.
Okay.
So, I mean, it was thank you again for inviting me. One reason I'm talking to you now is because, in the last 1 year, the people who work on Civl, including me, right? We work very hard to get Civl to a point where it can actually be usable by other people. Lots of work went into it. If you find anything that I said interesting and you are encouraged to take a look at Civl, it's great. I would love to hear about your feedback. Anything that you like about it, anything that you hate about it, anything that you would like to see improved in it. And if you want to work on open problems, let me know. Love to have a discussion.
Yeah, I have a question here. So
yes.
Any plans on using Civl for GPU programs or something, verifying GPU programs or something like this?
No, I mean, I don't have, I've been heads down just trying to make it usable, like the basic functionality usable. And like connecting Civl to good applications, it's an open thing. For that, collaboration with the experts in that application domain would be needed, because I mean, Civl is just a tool, right? It provides some functionality to you. Who knows how easily that functionality is going to be applied? It's only when you try to stress that tool with an application domain, like GPU programming is one. Another thing that I'm interested in, because I work at Meta in the core infrastructure division, is verification of building large verified distributed systems. So these are applications that are going to stress the tool, and they're going to give us feedback about what else is needed. If you're interested in GPU programming and you have some ideas, love to hear about that.
Okay, thanks.
So, Shaz, is there a good notion of refinement for concurrent programs? Like maybe for sequential programs is quite a bit of work, but I guess maybe you have some kind of a framework for refinement of this multi-threaded programs here. But
yeah, I do. I mean, so Civl has a notion of refinement. Everything is based around refinement. I like it. I was able to do a few things with it. I don't know whether you like it or not. It depends on what your notion of good is. But, I mean, if you don't like it, tell me about it. Take a look.
Right. I mean, there's these notions like serializability and,
So serializability is kind of related to these atomic blocks, because so one of the things, so serializability came out of
linearizability.
yeah. So these things, so serializability came out of databases. When you have concurrent transactions being executed, serializability says that, well, I want to execute them in any order potentially, but the effect should be as if each one executed in one step. So that's very related to atomic blocks. It's also what I'm doing in Civil is also related to linearizability, I would say, because linearizability is supposed to be composable. So the idea always with linearizability was that if you have a library and you have proven the operations in it to be linearizable, when you use that library in another context, then you can try to make operations there linearizable. And what I'm doing here is like that too, right? Because once you have atomic actions that are like the linearization actions for some library, now when you're reasoning at a higher level at the client, you can use as atomic actions and you can construct more atomic actions and then so on and so forth. So there are all those inspirations are somehow present inside Civil, but they are in a more general form, in a way that things could be transformed in a general setting to some kind of the reasoning machinery that we all know and love, type systems, flow analysis, logical reasoning, and so on and so forth.
Yeah, I mean, doing linearizability proofs is I've never been able to do one myself. And
so you can use,
but maybe these left movers, right movers help you there too.
Yes, they do. Yes, that's right, they do. So for example, one of the Civil samples that I can point you to if you're interested in is a proof of the Triber stack. So Triber stack is a somewhat tricky shared memory algorithm, fine-grained implementation of a concurrent stack, right? And so in the proof, you show how to convert that into a simple atomic actions which atomically push and pop from a stack.
Right.
So what's the latest going on in terms of verifying concurrent systems? Is it distributed protocols, concurrent data structures? What are people thinking about these days?
So you're talking about the broader thing, the broader community
that people are interested in solving.
Yeah, so I think it all depends on the application domain. So I am very interested in verified large distributed systems. So I work in the core infrastructure team division at Meta, specifically in their core databases team. And I mean, these are very large distributed systems with lots of implementations of protocols that are interacting with each other. We get production issues routinely when there are problems happening. It would be nice if the effort required to run these services in production was reduced, because we just have constructed them in a better way to begin with, or we have better tools to help debug problems and so on. So that's something that I'm very interested in pursuing. I think that I can imagine other sort of, if you will, grand challenges So you know that there is a large collection of, there's a Java util concurrent library. If you're interested in concurrency, fine-grained concurrency over shared memory, I think it could be a tremendous accomplishment if you could build that stack of libraries, in a verified manner, starting from low-level mutex primitives, then going up to lists, and then stacks, and then hash maps, and so on, and make that available. A publicly available verified replication protocol that has enough bells and whistles that people can just use it routinely, or a publicly available verified key value store, replicated key value store. All these would be amazing accomplishments, especially if they are done, if the verification is done in a way that is highly automated, so you can really treat it like software development. People are asking for features, you're able to quickly do those things and provide new features, still while making sure that the proof stays intact. GPUs are very, very important. Inside Meta, for example, there is a huge effort in improving programmer productivity for GPU kernels. If we can build some tooling to bear there, that would be awesome. That would be awesome.
So there are. Let me
Yeah,
just inject a couple of thoughts in there, right? So there are two things I have tried in the past but failed, and you can maybe tell me if with this technology there's a chance of trying again. So one is, so you mentioned distributed protocol. So we were looking at a distributed protocol running. It's a replication protocol. The trouble that we faced with that one was that the specification was not easy to write down. With almost linearizability, but not quite. And the trouble starts happening when you start specifying these corner cases. When it's not quite linearizability, you're not quite sure how to even write down the specification. And so what people have ended up doing in that context was that they use TLA for verifying a subset of the behaviors where they knew that there is linearizability, and then they applied a TLA to at least check that. And for the other cases, they will okay, well, they reasoned manually and then made sure that these corner cases, nothing bad will go wrong. It's not, some weird things will happen, but it's okay. Life goes on. So that was one challenge. I don't know.
So here you're saying the challenge is in coming up with the specification.
Yes.
So if for example, may I suggest this, that if you cannot prove linearizability, at least you should be able to write down some assertions that you always expect to be true, right? Or some invariants. That ought to be possible.
Yes. So correct. So the thing people did is to write down tests. So there will be tests for small scenarios, do this, and assert that finally at least something holds, some safety condition holds.
Excellent. Very good.
And
so now
you do testing.
Yeah. So I mean, if you can write tests, I think that you're already halfway to using Civl. Here's why. Because when you write a test, you have to create a complete system. You have to write the mocks for the external components. You have to write the test harness, which is generating the work. And you have to have a specification or the assertion. Now, the only difference between Civl and testing is that in testing, you artificially constrain the test and you make it artificially small. Whereas with Civl, what you can try to do is you can say that, okay, my test is very, very general. It can run for arbitrarily long. It can create arbitrary values of arbitrary size. And if your assertions are robust, then you should be able to verify, you should expect those assertions to hold even for such a general harness. Now, at that point, you have a civil verification problem. And the question is, well, how do you verify these assertions for such a
But I
general
think-
harness?
But I mean, when you generalize the harness, writing down the assertion becomes equally hard. No? Wouldn't that be the case? That now you have to think of for one, two insertions into a list. I can figure out, things will go in this order or that order, and you end up in this state or that state. But now if you ask me to write down something that holds in n insertions, I will not know how to even express it.
No, so I understand that, right? But the thing is that when people build, so you're talking about some kind of a component, right? So the idea is that people don't build components in isolation. They probably have some client in mind, right?
Yes, correct.
So what the way I would approach the modeling of the test and the specification is that I would try to imagine what a client would do, and what are the client's expectations, and then try to generalize from there. I mean, a client is not going to do just 2 insertions, right? The client is going to do arbitrary number of insertions, and yet the client is expecting something. What is that expectation? You got to know that, right? Does that make sense, Akash?
Yeah, it makes sense. I mean, in theory.
So what is this example? If you can share it with me, maybe I can think about it.
I can, I'll try to find a link. I think it is open source.
Okay.
Yeah, I'll try to find a link and send it to you.
Okay.
And how do you imagine, all this, the set of all tools in this operating in this space, right? There's TLA, IV, Armada, a bunch of these things. Is there any story? I mean, at least in the sequential world, you have things like Lean and F-star, Isabel, that have huge communities of people just writing more and more verification code, more and more verified code. What about concurrency? Do you see any of these things providing the foundation of a programming system that a lot of people can use?
No, I would say not at the moment. Not at the moment. I don't think we are quite there yet. So I think that the tools that you are talking about, right, Lean and F-star, the people who are using them, they are still mostly researchers, and they are using those tools to write some code because they are just interested in pushing the state of the art in verified software. I think that with concurrent systems, we are a little bit behind there. So there are examples, like the Iron Fleet is a good example. Even with IV, there is code generation. But I still feel that it's we don't have enough experience and enough tooling support to get this all the way. Even with Lean and F-star, for example, right? I think that there's a lot of scope for improvement in terms of the interface that is provided. So the idea is not to write verified programs and basically collapse as a result of the effort. It has to be sustainable. The tools have to be to improve, right? And your productivity for writing code has to improve. Even with the Lean and F-star and all these things, I think that the productivity is very, very poor. And part of the problem is that I think that all these tools, no matter what they are, including Civl, they are all very, very general. I don't think we are going to reach high enough productivity for these things to be truly useful until we specialize things.
Specialized
It is possible that, yes, it is possible that maybe in 20, 30 years, we will have general purpose verification-oriented programming languages that will work for across domains. We are nowhere close to any of that. We'll
Yeah,
get there. Yeah.
Is there a reason concurrency comes in the way? Like in F star, one thing, I mean, yes, mostly, people in the research domain use it. But one thing that is good is compositionality. So I can write some F star code, you can write some F star code, and we can call each other and build bigger systems. Concurrency compositionalities may be harder. Putting things together and having people verify separate parts and then somehow putting things together, that's harder. Without
I mean, for sure, that is harder. For sure, it is harder. So, for example, I did not even touch upon, even with Civl, right, or even of the other things that tools that people build, this idea that verification of a large program can be broken down into components which can be developed independently, right? We don't have that yet, right? Iris, for example, I'm sure people who come from the functional programming community, they tend to pay attention to modularity from the very beginning. So it's possible that some systems have that. But I agree with your assessment. I think that this idea of putting things together in a way that is robust is we are even further away from it when concurrency is involved. When concurrency is involved. However, I want to reiterate what I said earlier about productivity. Okay. So in a way, there is no new problem, right? It has been possible to construct verified systems by a lot of effort for years, for decades. If you look at early work on ACL2, when Boyer and Moore invented, these theorem provers at UT Austin, they wrote all these papers, right? About how do you construct an OS and how do you construct blah, blah, blah. I don't even remember, right? So that story just keeps going on and on. So if they managed to do it 50 years ago, does that mean the problem is solved? No. I mean, if they're solved, then what the hell are we doing here, right? Why are we writing all these other papers? So just because it is possible to construct a verified program by a lot of effort doesn't mean that the problem is solved. You have to keep working on the productivity.
Yeah, makes sense. So any other questions that have taken up too much time?
More questions?
I have one question if there's time. So
I have time, I can keep going.
okay, sure. So basically you mentioned about verified program construction being the next holy grail in some sense. I mean, in the sense, if instead of making one person write a program separately and the other person verifying it, if you can move towards verified program construction, that'd be something good. I mean, it seems too good to be true in some way because it doesn't seem very easy, but would you, I mean, more specifically on, I think, layer inference, right? And or verified program construction, can you tell us what's the current state in Civl, or what's the aim that you're looking into, the goal?
The goal for layer inference, you mean?
Yeah, layer inference and verified program construction in general.
Okay. So I think, so let me talk about layered verified program construction. I believe that the path forward is, first of all, everybody needs to get on board. That we stop talking about, just like nobody in the right mind talks about automatic programming. Nobody should talk about automatic verification, okay? Because as soon as you do that, you start wandering off in a direction that I don't think we need to go into now, based on all the evidence that we have accumulated in the last 2 decades. That's the first thing. Second thing is that I think that the way we make progress is by focusing on an important domain and taking a lot of general machinery and trying to customize it while making sure that for that particular domain, we are able to tackle a large swath of problems, okay? And productivity is the key thing. It's not enough. It's not enough to say that, okay, I constructed this one program by a lot of effort. No, that's not how we're going to measure progress. The way we are going to measure progress is by inventing the tool chain, building not one program, but multiple programs, and being very honest in how much we improve productivity in the construction of these programs. And then we try again. So I think that the path to productivity lies in specialization for important, useful domains. And when you do specialization, I'm sure you'll be forced to invent new techniques. So that's not to say that we don't need more work, foundational work on general techniques, but I'm saying that there has to be also part of the community working on connecting the dots and focusing on the end-to-end story for a particular domain. Now, as far as, did that help about the general picture?
Yeah, that makes sense. Yeah, thank you.
Okay. For layer inference, I mean, that's a very focused problem. What I'm looking for is just like we have layer checking right now, Civl already does layer checking. That is, to me, it's the analog of type checking. And what I want is the analog of type inference. Now, what that would look like, I have no idea.
Okay. Yeah, thank you.
Hi, Shaz. I am Alvin. I have a general question on how different is the concurrency of multi-threaded versus distributed, and can Civil handle what's the difficulty in moving from multi-threaded to the?
So you're asking whether maybe you're asking several things. You're asking, is there a difference between reasoning about multi-threaded systems versus reasoning about distributed systems? Maybe that's one question. The second question is, can Civil reason about both? Which one should I try?
The first one was.
Yeah. So I think that there is a difference. Well, yes and no. So there is no difference, and then there is a difference. Why is there is no difference, right? So the thing is that if you consider TLA plus, are you familiar with TLA plus?
Not very much.
Okay, never mind. Are you familiar with a Turing machine?
Yes.
Okay, so you know that every program can be represented as a Turing machine. Any Turing machine can be represented as a transition relation.
Yeah.
Once you have represented something as a transition relation, you can prove invariance.
Mm-hmm.
So in a way, a transition relation is just like a shared memory program. The Turing tape is shared memory, right?
Mm-hmm. Okay.
Okay. So the thing is that everything is possible at the same time, nothing is possible, right? Why is that? It's because, the thing is, you have to make it natural. You have to make it easy. You have to make it productive. That's where the domain, whether it is multi-threaded, whether it is message passing, whether it is distributed systems, comes into play and becomes very, very important. You have to invent techniques that exploit the peculiarities of a particular domain and the constraints, and use that to optimize productivity. So for that reason, I think that there will be a difference between tools that are targeted towards low-level multi-threaded code that are trying to exploit the resources on a single node efficiently, right? And protocol implementations that are spread across distributed systems. So you need shared machinery for both, but I think that there'll be specialization also.
Mm-hmm. So like coroutine with Go, etc., they are pushing to something away from the standard threading model. Like they are pushing to a coroutine model where maybe some of these issues don't happen anymore. Like,
So with the coroutine model, the way I understand it is that when the coroutines are running all together, they're running in parallel, there's explicit yields. So you cannot be preempted, you yield voluntarily. So I think that the advantage you get is that you don't have to worry about interference. You have to worry about interference only at a yield point. So that's nice, but you still have to worry about interference at a yield point, right?
Okay. So one side of the track, maybe like, are we like overusing the threading model, like for where it doesn't make sense? Is that what makes the multi-threaded program so complicated to begin with? Like, or should we restrict multi-threaded programs to a specific subset of the domains for work?
Why not? Sure. I mean, I think that if you can carve out a domain where a restricted model is able to give you the right kind of expressiveness, and you can exploit that restrictive model for more productive tooling, that's a great thing to do.
Okay. I think because the coroutines never was popular until like 5 years ago. So most of the programmers only had multi-threading libraries available with them. So they threw any problem by trying to solve it using multi-threading essentially. But maybe that was a lack of capabilities in the programming language itself at that point, which has created this complexity in the software. So if some of the problems may be better matched to coroutine model. So if we move to that, probably some of these multi-threaded related issues won't even occur in the software.
It's possible. I mean, low-level race conditions will not occur. Most likely, you don't have to worry about weak memory models. Those are big problems that can be eliminated, I suppose.
And in the distributed one, is that the queues and delays, is that what makes it difficult for the regular concurrency models to handle? Messages.
So, I mean, it depends on what you want to do. I think that if you don't, in most of the stock, I was assuming that you are trying to do something like prove safety properties, the kind of thing that you want to do during testing. If your goal is not to be as expressive as that in verification, then you can, supposing you only want to prove absence of races or deadlock freedom, then I think lighter weight techniques could work. That's another dimension of flexibility, by the way, where a lot of classical work in programming language design targeted towards concurrency actually does not focus on general safety properties. They are trying to restrict the kind of guarantees that they provide, and as a result, try to provide more automation. Rust is actually a good example. So Rust is fairly mainstream, I would say, fairly successful language. And it gives you, if you stay within the safe subset of Rust, then you get race freedom by default.
Okay. Cool. Okay, thanks.
So you mentioned that you are working, probably you have plans to work on improving productivity for GPU programs. What are the productivity hurdles that you see for programming for GPUs?
So for GPUs, I'm not that familiar with the domain myself, but I think that you know what? I better not say anything here. But if you want, I mean, I can dig up some resources here. There are people, you know what you should do?
Yeah,
Just a
yeah.
comment to the organizers. You should get Alistair Donaldson to give a talk at this forum and tell him that he should tell you guys about programmability and verification challenges for GPUs. I bet he'd give an excellent talk.
Right.
Alistair Donaldson is at Imperial College.
Yeah, I think his paper was the GPU verify paper.
Mm-hmm.
So yeah, if there are no more questions, Akash, should we wind up?
Akash has
sent
dropped
you a
off, I
message.
think.
Yeah, he sent you a
Okay.
message saying it's your job to wind up.
Okay. Anyway, thanks a lot, Shaz. Yeah, great talk, and thanks for handling all the questions across various topics, philosophical from different points of view. So thanks.
All right.
Yeah.
Okay. Thank you so
Bye,
much.
Shaz.
Thanks again. Bye-bye.
We'll
Bye-bye.
take up
See you.
your advice of asking Alistair next for the next talk.
Awesome. Bye.
Okay. Thanks.
Bye.
Thanks, everyone. Thanks for joining. Yeah.